So now we're ready to go deeper. For students who need materials to practice, you could use for the maths SS1, SS2, and SS3 textbooks. So we're now at mathematical induction, and we are starting with the definition. It has to do with proving that a statement is true. Statement or proposition Pn to be true for positive integers n. Okay, so we have two major steps: the base step, also known as the first step or basis step, and the induction step. So what happens is that we go for Pn, we take the statement Pn, and we then prove for n equals to 1, assume for n equals to k, and then prove for n equal to k plus 1. Well, you can pause the video and read all that has been stated here mathematically, but the summary of it is that we're just proving those two major inductive steps. Okay, so let's go dive in. So same here, you can pause the video, read to understand what I've summarized in a brief way, just so that the video will not be too lengthy for you. Okay. Okay, so this is the first example we're considering. I told to use the principle of mathematical induction to prove that this sum is same as this. Okay. So what we do is let Pn be the statement, which is exactly what you have here, right? So let Pn be that statement. So the deductive steps again are the base step, right? The inductive step, induction step. Okay, so the base step is for n equal to 1. So that's why we're checking the base step for n equal to 1. Now for n equal to 1, we need to consider both the right-hand side and left-hand side and prove that we'll get the same solution whenever n equal to 1. So we check if this left-hand side is going to be same as my right-hand side by simply plugging in 1 wherever there is n, 1 wherever there is n. So on my left-hand side, you can see the sum is going from 1 to 1, meaning that r is simply just 1. It can't go beyond 1, right? So that's all to it. The left-hand side will be equal to 1. For the right-hand side, again, wherever you see n, you plug in 1. You substitute 1, so you see 1 is everywhere here now, wherever there was n before, right? Wherever there was n exactly. So these 2 points right here. Okay, so if you simplify further, you see here you get 1, 2. So you can see that the left hand side equals to the right hand side. So P1 will be true. So we've chosen P1, so we need to assume, because that's the inductive step, which is we're going to the next induction, step, right? So we assume for n equal to k. So we go straight to the next slide. So for next slide, we're going to assume, right, for n equal to k. So we can see that it's pk there. So we assume it's true. So what happens is that because it is true, wherever you see n, what do you put there? You put k. So wherever there's n, now there will be k. This n here, this n will now be k, bracket k plus 1 all over 2, right? So let's see. So we have assumed it to be true. It means my left-hand side will take the sum all the way to k, and this will be the sum, right? And my right-hand side will just simply be k into k plus 1 all over 2, which is what you see here. So meaning that this sum is same as this sum, which is what you see here, is same as this, which will give an equation because we are assuming this to be true. Okay, so we have the sum for n equal to 1 to be true, and now we have assumed that pk will also be true. So what happens? We need to now prove the final inductive step, which is that pk plus 1 is true. We have to show that. So to show that, we check the left-hand side and confirm that it is the same as the right-hand side. So to check the left-hand side, we take the sum from 1 to k plus 1, right? Because wherever we see n, now we're plugging in k plus 1. So the sum will keep going from 1 to k plus 1. So we know it stops with the actual equation, the actual formula runs from 1 to n, right? And the sum was, the formula was going from 1 plus 2 all the way till you get to n, right? Sorry, the screen is shaking. So all the way till you get to n. Well, n now is k plus 1. So your sum keeps going. And this before you get to k plus 1, you must have gotten to k, right? So that's why you can see k plus 1 is here and there's k here. Okay, so if there's k there, you can see something. Because we need to solve pk plus 1, right? So we need to solve pk plus 1. To solve pk plus 1 now, you can see here that this sum here, right here, this one, you have seen it before. See it over here. And we know it's the same as this. By this equation, we had numbered it. That's your assumption, right? So what happens? Wherever I see the sum, I'll put in this value because I know it's the same as this. The two of them are the same. So you can see what I've done here. Wherever this sum is, all the way to k, this is here. The plus remains, see it here, and the k plus 1 remains, see it here. The reason is because this allows me. Okay? Okay. I haven't done that. To simplify this, you can see over here, this will be over 1, right? All over 1. The LCM of this term would definitely be 2, right? Because this is 2, this is 1, right? So if the LCM is 2, 2 into 2, it will go 1, right? And 1 times the numerator will give me this numerator here, right? 1 into 2 will go 1 time. Sorry, it will go 2 times because 1 into 2 will be twice, right? To go 2 times. Let me return my 1 there. Okay, so it goes 2 times, so that will be 2 times my numerator here. That's why you see 2. There's a plus sign, right? There's plus, and then there's 2, and then there is the k plus 1. Okay, so now you now understand how I got this part here. So if you simplify further, something is common to this numerator. So the denominator remains 2, 2. But look at this very well. Something is common to both terms, right? There's k plus 1 here. There's k plus 1 here. So I can pull out k plus 1. What am I left with? K and then plus 2. So that's why there's k plus 2 here. So we finish simplifying the left-hand side because there's nothing we can do. So we need to know if it's the same as the right-hand side, right? So remember this. It is k plus 1 all over k plus 2, right? So let's move forward. So inductive step continues now. We need to prove that the left-hand side is the same as the right-hand side. But remember what our right-hand side was. It was n. Let's go backwards. Let me help us find it. The right-hand side by the question we were given was this, n into n plus 1 over 2. So wherever we see n, we're plugging in n plus 1. So again, the right-hand side was n into n plus 1 all over 2. But wherever we see n, we put k plus 1. Wherever we see n, we put k plus 1. You can see the k plus 1 here and k plus 1 here. And then there's the plus 1 here, which is the plus 1 over here, right? And then the 2 in the denominator. Okay? Okay, so if we look at it simplifying further, we can see that this is simply k plus 2. That's why there's k plus 2 here, right? So we found the right-hand side. The right-hand side is this. Right-hand side is this. So what was our left-hand side? Left-hand side is this. Are they the same? Yes, they are. So left-hand side equals to right-hand side. This means that pk plus 1 is true. So what will you then conclude? You've concluded, you've checked for p1, you've assumed pk, and you have seen now that pk plus 1 also is true. This was true. This was assumed to be true, and this turned out to be true. Therefore, since the basis step and the inductive steps have been verified, it follows that Pn is true for all integers n, and the inductive proof is complete, which means that you've completed the proof. So that's also the proof of that particular question given. Okay, you can simply just say since P1 and Pk, P1. So you can make it easier for you can just say since P1, Pk, and pk plus 1 holds, it follows that Pn is true. That's all. Okay, let's move forward now. So now we have another question before us. Says we should prove using induction that 4 to the power n minus 1 is divisible by 3. Now this is a little different for n running from 1 all the way to infinity. It doesn't end. Okay, so we want to prove that this statement is true using induction. Again, the inductive steps would be followed. We check for P1, assume PK, and prove PK plus 1. So we start with the first one, which is n equal to 1, as you can see here. So for n equal to 1, you can see that we have 4 to the power power 1 minus 1, because the power is n is 4 to the power n, right? So wherever there is n, you plug in 1. So that's why you have 4 to the power 1 minus 1. And that's just simply 4 minus 1, because 4 to the power 1 is 4. And if you subtract 1 from 4, what's that? That's just 3. Clearly, 3, which is this answer, divided by 3 is 1, meaning that 3 divides this 3 value you got, this 3 you got. Hence, clearly the final answer, 3, is divisible by 3, meaning that P1 is true. Okay, so that's just what we have done there. Okay, so let's move further. We've checked for P1. We need to assume PK and prove PK plus 1. Okay, so next is the inductive step itself. So wherever we see n, remember the question is 4 to the power n minus 1, right? We want to check that it's divisible by 3. So wherever we see n, we're plugging in k. So that's what you have here. So we're going to assume. So assume pk is true. So this will be true. That's why we have labeled it, just like we labeled the previous one we had for the sum, right? So we then proceed to prove, because we need to prove the next step, which is for pk plus 1. Wherever we see n, we're putting in k plus 1. And you can see, and you can see over here that wherever there was n, we've plugged in k plus 1. By indices, if you have a raised to the power m n, I'm sure you remember your indices, this will be the same as a to the power, that should be a, not the product. That will not give me what I want, but m plus n, right? For those that remember the indices, that would be a raised to the power m times a to the power n, right? Is that not what you did? Okay, so in the same way, using this law of indices, that's what was applied here. So I have 4 to the power k plus 1. That's simply going to be 4 to the power k times 4 raised to the power 1, though the 1 is not written, right? So that's how I got what you can see that this breaks down to this by indices. And you have your minus, and then the 1 and the 1, right? Okay, so with that, if you now look inside the bracket, our goal is to show that it is divisible by 3. Is that not what we're saying? Divisible by 3. Divisibility by 3 is what we're looking at. So we look into this. How can I express this? Because I don't need to disturb 4k minus 1. You know why? Over here, I have assumed that this is true. This will hold for anything whenever I have 4k minus 1. So the only thing blocking me in this particular one here is the 4. So I need to find a way of expressing 4 in such a way that 3 will be inside it. So I want to write 4, and I want 3 to be inside it. The easiest, and it's not a product actually in this particular case, because if I must write it in such a way, a sum of 4, that 3 will be 3 plus 1, or 1 plus 3, right? So whichever one you want. I've chosen 3 plus 1. If I do 1 plus 3, it will still work anyway. But let's go ahead and use what we have now, so that it will go be the same with what you see on the screen, right? Okay, so wherever we see 4, we plug in our sum, 3 plus 1. So that's what you see there. So there's 3 plus 1 in place of 4. The minus is still there, minus, and the 1 and 1 still there, right? Okay, we open our bracket. If we open our bracket, 4 to the power k times 3 will give us 4k3. And 4 to the power k times 1 will give us this 4k times 1, and our minus 1 still remains there. Okay? So if we look at it, this term here, if I rewrite it properly, this is simply saying 3 times 4 to the power k. And this term here, this 4k times 1 is 4k to the power k minus 1. You have seen this term before. See it up here. See it right here. This one is divisible by 3. And this one is 3 times some values, and which is a multiple of 3, right? Meaning that it is divisible by 3. And we already know that 4 to the power k minus 1 is divisible by 3. Hence, this statement, when n is pk plus 1, okay, means that it holds, it's true. Okay. So since the basic step, the conclusion as before, we conclude that the statement is true, it's divisible by 3. And that completes the proof, okay? So if I was fast, you could go through the video slowly, just pause as you continue. Thank you.